So let's now investigate the interactions between pH and solubility. We've looked at the previous equilibrium, where we're taking calcium fluoride and breaking it into its composite ions. We had a KSP for that, which I've already forgotten. Let's scroll up and find out. KSP for this particular thing was 3.9 times 10 to the negative 11. Great. We also see that we can mess with these ions by introducing pH changes. We know that calcium fluoride produces a weak base. The fluoride ion is that weak base. And so, if we add acid, we can react that weak base and take it out of solution. Just like with forming a complex ion, we're going to be able to remove that from solution by adding in some acid. So if we take some acid and add our fluoride ion, we know that that equilibrium is producing HF. This is going to be the reverse of the Ka, right? This is essentially a Kb, right? So we can go ahead and use that. We can say this is 1 over Ka, or it's simply the reverse reaction, right? Ka for hydrofluoric acid, we're going to go ahead and go to discord and find that. Remember that we have our extra resources that has all these tables. So here's the KSP one, here's some KB ones. Let's look up A for hydrofluoric acid. There it is, 7.2 times 10 to the negative 4. So notice that's 1 over Ka because we have the inverse of the reaction. So we reversed it. But the point is here, when we add these together, we're going to be able to get rid of some of those fluoride ions. And in fact, we're going to want to multiply this equation by 2 so that we can get rid of them. And remember, when we multiply an equation by 2, we're going to have to square our Ka. So this was exactly on your exam, right, where we looked at doing the inverse and doubling of a reaction. So we'll have that. All right, so when we have this now, we're going to combine our reactions. We're going to get CaF2 plus 2H plus 2F minus turns into Ca2 plus 2F minus plus HF. And again, we're going to have our F minuses will be the same on both sides. So by adding in acid, we're going to be able to increase our solubility of this compound. And just like before, if we add the equations up, we need to multiply the K's for this. So our new equilibrium constant will be equal to KSP times our 1 over Ka squared, because we had to do the reverse reaction as well as multiplying it by 2. And so we're going to have 3.9 times 10 to the negative 11 times 1 over 7.2 times 10 to the negative 4 squared. Let's go ahead and do this. So we have, I'm going to do the Ka part first because I'm sure I'll mess that up. So 7.2 times 10 to the negative 4, we're going to raise that to the negative 2 power. And now we're going to multiply that by 3.9 times 10 to the negative 11. And we get the new Kc is equal to 7.52 times 10 to the negative 5. So that's our new equilibrium constant for this reaction. And so let's say we're going to add some HCl. Let's say we take our calcium fluoride and dissolve it in, I don't know, let's say in 0.1 molar HCl. All right, so again, we have our concentration of acid. The chloride isn't going to do anything, so we don't have to worry about that. This is solid. We have our original concentration of hydrogen ions. We have 0 of our other 2 products. We're going to be subtracting X. I'm sorry, this should be a 2 here. And we're going to have two HFs as well. So we'll have X, we'll have 2X here. So the equilibrium constant for this, Kc, would be equal to X times 2X squared over 0.1 minus 2X squared. Again, a pain in the ass to go and figure out on your own, right? Wolfram alpha to the rescue. And of course, this would be equal to the equilibrium constant that we calculated, 7.52 times 10 to the negative 5. All right. So, bust out thy widgets. Here it is. We're going to plug this in. So, x times 2x squared divided by 0.1 minus 2x, also squared, equals to 7.52 times 10 to the negative 5th power. Let's see what we get, and let's hope I've plugged this in properly. It looks okay. And of course, it's clearly this 47 minus... Look at these crazy numbers. Why can't I just give you the decimal right away? All right, there we go, 0.005. Again, our other numbers appear to be imaginary, so let's stick with our normal numbers here. We get 0.005. And so that would be the concentration of our calcium ions here. So if that's what we are solving for. I don't think I had technically asked, but that would be our concentration of calcium ions. If you remember way back to when we originally did our common ion effect problem, we saw that for pure water, we're looking at 2.1 times 10 to the negative 4. All right, and now we have 5 times 10 to the negative 3. So we've increased it a little bit. All right, so the acid has helped out a little bit. The reason that it's not helping out as much is because this equilibrium for the acid is not as strong as it would be for Kf. Equilibrium constants for formation constants can be like 10 to the 31st power. They're like incredibly high. So we still see an increase in the solubility, right? We've dissolved more calcium ions than we have before. So it's certainly possible. And while we're not going to do problems on this, we're going to see that the pH, or rather acidity, helps dissolve many basic salts. So those would be hydroxides, like nickel 2 hydroxide, we would consider insoluble. But in the presence of acid, we're going to react away some of those OH minus ions, which will go ahead and push us towards making more products. So many salts that have hydroxides or oxides will be able to dissolve in acidic solution. But that's not necessarily only hydroxides and oxides. We also have things like the calcium fluoride, because fluoride was a weak base, right? So anything that has a weak base will dissolve a little bit better in the presence of your acid. So something like calcium carbonate as well would dissolve in acid. And again, it's because the equilibrium is taking away a product, allowing your reaction to go forward more and more, producing more products through the Chavier's principle. By contrast, we'll see that the opposite is true for basic solutions. Basicity helps dissolve acidic salts. So, for example, if you were to have a salt that is acidic, you've got a cation on there that is, for whatever reason, being insoluble. Say we have cadmium bisoxalate or something. The oxalate ion there, or the bioxalate ion, is acidic. You can tell that by the Ka of it. Putting this with a basic solution would help dissolve it. So you can do that. It's a little bit less common to see this, but if you have an acidic salt, adding more OH minus can help. And interestingly enough, OH minus is a strong Lewis base too. So it can form complex ions with certain metals. For example, aluminum hydroxide is insoluble in pure water, not going to dissolve. However, if you add a hydroxide ion to it, it forms you add a fourth one on there, and I have the KF for this here somewhere. It's incredibly large. Let's see, it is 1.1 times 10 to the 33rd power. 33rd. Very, very favorable. So aluminum hydroxide is not soluble in water, but in even slightly basic conditions, it will dissolve very easily. This is an extremely large KF. And because aluminum hydroxide has hydroxide on it, it will also dissolve in acidic solution, interestingly enough. If you add H+, you're going to be making aluminum ions and water. So that's also favorable, right? Because H plus OH minus makes water, takes the OH minus out of solution, and we're able to get more to dissolve this way. So aluminum hydroxide is amphoteric as a salt, is an amphoteric salt. So it dissolves in both acidic and basic solution, just not in neutral solution. So just be aware of that. So basic salts dissolve in acid. Acidic salt, although there are not too many of them, would dissolve in basic solution. A little bit more, right? You can do the KCs for those. And we just need to remember that hydroxide is a strong Lewis base and can form many complex ions. If we take a look at the KF table, I'll put it closer at the end here, but if we want to just take a look at some of these, although they are all to the left here, let's see what we can do. We're going to see that hydroxide is a component of many of them. So, for example, this chromium with 4 hydroxides, very, very soluble. We see that we have, what else do we have here? The lead with hydroxides, very soluble. 10 to the 14th is your equilibrium constant. Zinc down there, 10 to the 17th power. So a lot of these complex ions do work well with hydroxide. So you can change the pH of these to get them to dissolve better. And that's also very useful for separating things. You'll have a lab on this where we will separate things. For example, AlOH3 dissolves in acid and base because it forms that complex ion. And it could also dissolve in acid because it's a hydroxide. Iron 3 hydroxide, however, does not form a complex ion. It doesn't form a complex ion with hydroxide. And as a result, does not dissolve in base. So, if you're trying to separate aluminum and iron from each other, even if they're just regular ions, you can turn them both into hydroxides and then keep making it more and more basic. Your aluminum will redissolve, but your iron will precipitate out. And you can separate your iron this way. And then you can go ahead and separate your aluminum later. So these solubilities allow us to be able to separate elements from each other. And that's incredibly important, industrially speaking. If you are mining ores, for example, many of them contain many minerals. And if you only want to get the iron out, then you don't want the aluminum, although I think aluminum is more expensive, question mark, don't know. you can separate them using chemistry. And so that'll conclude our investigation into equilibrium. We're going to next talk about thermodynamics and how energy and energetics play into all of the processes we're seeing so far in chemistry.